and welcome to today's crash course on electrical circuits. So this content is meant for secondary 4 students. So we're going to divide, there's so much stuff to talk about. So we're going to divide the content into 2 parts. The first part is going to be the components that make up an electrical circuit. We're going to talk about the 2 different types of circuits that exist and properties about those circuits. So current intensity, potential difference, and resistance. And then in the second part, we're going to talk about the formulas that we use to find those properties. So before we jump into electrical circuits and the drawings and the diagrams, let's talk about what an electric circuit actually is. An electrical circuit is a combination of electrical components connected to allow the flow of electric current. And if we want to just take that a little further, electric current is the movement of electrons through a conductor. So when we think electricity, we have to think electrons. So when we talk about electrical circuits, we need to know about the different parts that make up an electrical circuit. And so we have a table here, and we're going to talk about the component, the symbol, and its function. And we've taken the ones that are the most commonly used that you will see in your secondary 4 lives. And so it's really important to kind of get familiar with these symbols and what they do. So the first thing we're going to talk about is the battery, because every single circuit needs a power supply. And the symbol for a battery is this short line and a long line. So this would be our negative and our positive, because every single battery has a negative and a positive end. We also could sometimes see where a battery is connected to another battery. So sometimes we can have 2 batteries together and they look like this. So we have our negative, our negative, and our positive sides. And remember that a battery is the power source for all electrical circuits. They can't function without that because it produces the electrons. Now we also have our wires. Now wire, basically just a straight line. That's the symbol. Anytime you see a straight line, we assume it's a wire. Wires can be made out of lots of different metals. So we can have gold or silver or copper. And so gold and silver are a little bit more expensive. So something that's more economical and cost effective, we use copper. Copper is usually one of the primary conductors that is used in a circuit. The next component that we can talk about is the switch. And a switch can either be open or closed. And so a switch looks like this. So we have our wires going in and then we have the switch. Now this switch is open, and a switch that is open will stop the current from flowing. So when we deal with that, you'll see it like this. It'll have an arm up like this. Now if a switch is closed, you're going to see it look kind of almost like a straight line with two balls there. See, like this? When a switch is closed, it means that the current is going to flow easily around. So it's in a function. Then we have a resistor, and a resistor is used to regulate the flow of electric current. And a resistor just looks like this. Anytime you see this, you know that it is a resistor in our circuit. Now we're getting into the components that actually are the functions of a circuit, why circuits exist. And they are to produce certain things. So we want to transform electrical energy into something else. And so we have our light bulb. So you'll see a light bulb symbol. It looks like a light bulb. Okay, so our light bulb symbol is actually a really great example of a transformation of electrical energy into light energy. So then we'll talk about the sound device. So a sound device, again, is another element in a circuit that transforms electrical energy into sound energy. And the symbol for our sound device is going to be a point with a circle around it. So that is our symbol for our sound device. And then finally, the motor, again, another circle with an M. So these are our symbols that we're going to be familiar with when we're dealing with our electrical circuits. So let's draw an electrical circuit and see how these all come together. So taking into account the components that we just saw and the symbols, we're going to draw a circuit. So we're going to start with our power source. That's always the first thing that we need to do. So we have our battery. Okay, we have our negative and our positive side of our battery. And it's going to come down, and I'm going to connect it to a switch. And this switch is open. And then I will connect it to let's pick a light bulb. Then it's going to circle around back. So here I have many components. I have my conductor, Okay, so I have my light bulb, I have my power source, and I have my switch. Now in this case, the switch is open, which means that electrical current is not flowing. But if I were to close it like this, then I know that electrons are flowing through. And so we know that our electrons are going to be going around through the light bulb, through the switch, and around to the positive. What is the conventional direction of the electrical current? Is it A, from the negative to the positive terminal, or B, from the positive to the negative terminal? The answer is B, from the positive to the negative terminal. So this might seem really confusing, but the explanation is actually quite simple. A long time ago, when scientists were first studying electrical circuits, they thought that it was protons that were going around in a circuit this way. And so they believed that that was the conventional way that electricity was running around. But now we know that it's electrons that flow through the circuit. So now let's talk about the different types of electrical circuits. And there are two, series and parallel. So the first one that we see here is a series circuit. And as you notice, all the components are connected one after the other to form one closed loop. So there's only one path for the electrical current to get through, which is really important because if one of the items, one of the components in an electrical circuit stops to functioning or malfunctions, the entire circuit is disrupted and it does not work. Then, if we look at the other side, we have a circuit that's in parallel. And that means that the components are connected with branching points to form several closed loops, which means there are several paths for the electrical current to get through. And so this is really important when we think about Christmas lights. So back in the day, Christmas lights used to be in series. So if one light bulb went out, all the light bulbs went out. And then you were hard pressed to figure out which one didn't function right. But now all Christmas lights are connected in parallel. So if one light bulb goes out, the rest of them can still continue functioning because it's just that branch, that one loop that doesn't work. Which of the following statements is true? A, in a series circuit with a light bulb and a motor, it is possible to turn on the light bulb without turning on the motor. Or B, in a parallel circuit with a light bulb and a motor, it is possible to turn on the light bulb without turning on the motor. And the answer is B. So here we have different circuit diagrams, and you can notice that circuit diagrams are usually in this kind of square shape. Keeps things organized, even though we know that in real life circuits kind of flow every which way, and circuits are actually quite bendable and pliable. So here we keep them as much as possible in these nice square forms. So let's look at our series circuits that are drawn here. So here you can see that we have two light bulbs attached to our battery, and then we have a switch that is open and a switch that is closed. Here at the bottom, same thing. Again, we have a switch that is open, a switch that is open and a switch that is closed. And whenever that happens, whenever there is a switch that is open, remember, the current is disrupted, and in a series circuit, there's only one path for the current to go through. So if there is not that continuity throughout a circuit, nothing's going to work. So no matter where you place the circuit where you place the switch in a series circuit, as long as if it's open, it's not going to work. But if we look at a series in parallel, it's a little bit different. So if we look at my switch number one is connected to the first branch that is connected directly to my power source, okay? So if the switch is open, that means that there's nothing coming around. The circuit is being disrupted, I should say, okay? Which means that if the circuit's being disrupted, it's not going to make it to the second branch. So nothing is going to work in this circuit, okay? No matter, even if that switch there is closed, it doesn't matter because this switch here is connected to the branch with my power source. So this branch with the power source is being disrupted, not going to work. But if I look at my next diagram here, my switch is closed, so the circuit's flowing through the first branch, which means that my light bulb is going to work. So it's flowing. But then I also know that the circuit, the energy flow is going to come over here, but my motor is not going to work because the switch over here, switch number 2, is open. So here, the light bulb is going to work, but the motor is not going to work because the branch with the motor the switch is actually open. So the current flow is being disrupted. So this is a really cool thing about parallel circuits because you can put multiple different objects that are connected. So in this case, I have a motor and I have a light bulb, which is kind of nice, like in places like bathrooms where if you turn on a light switch, the same switch is going to be connected to your light. And it can also be connected to your motor, or you can have them on two different switches and turn one on and not the other. So it can come in handy. So now let's talk about the different properties that we can play around with when we talk about electrical circuits. And the first one we're going to talk about is current intensity. So the number of electrical charges that pass through a given point in an electrical circuit per second, that's current intensity. And the mathematical symbol for current intensity, whenever we look for it, is I. Okay, so when we're looking for current intensity, which is the amount of electrons, we're looking for I. And the unit is amps or amperes. It's measured by what we call an ammeter that's connected directly in series to a circuit. So here is my ammeter. This is the symbol for an ammeter. It's an A with a circle around it. And as you can see, it's directly in my circuit. And I like to put it near a power source because that's where the electrons are coming out. So it's going to give me that measurement, but it doesn't really matter where you put it in the electrical circuit. And the symbol for amps or amperes or amps is A. So we're going to do a couple of examples with this. But before we get into any real examples, which will be in video number 2, let's talk about another property that we can solve for, and that is potential difference or voltage. And potential difference is the amount of electrical energy transferred by one charge between any 2 points on a circuit. And so the mathematical symbol, because we're used to seeing it, is V. And the unit is volts. So you've probably seen voltage around places. And it's measured by a voltmeter. Now, the cool thing about a voltmeter is it's connected in parallel. As you can see here, it has its own branch, okay? And what I like to do and what you should be doing, because we're talking about potential difference, is we want to make sure that it goes around a light bulb or a resistor or a motor. We want to make sure that it goes around that component so that we can measure the difference between the quality of the amount that goes in and the amount that comes out for electrical charges. And so we put our voltmeter here. So it's a V with a circle around it. That's the symbol. So you know that it's a voltmeter. And it's connected in parallel around one of those components that I mentioned before. The electrical symbol is also a V. So it's not that confusing. So the last property that we're going to talk about is resistance. And resistance is the ability of the materials to resist the flow of electric current. And so the mathematical symbol for resistance is a capital R. And the units are what we call ohms, which leads us to our next question. How is the value of resistance determined? Is it A, it is measured directly by a resistor connected in parallel? B, it is measured directly by a resistor connected in series? C, it is measured directly by a multimeter connected in parallel? Or D, it is calculated based on the current intensity and potential difference? The answer is D. So unlike current intensity and voltage, resistance has to be calculated. We need to do a little bit of math. So if you'll follow me over to part 2, we're going to hit up all of these formulas and do a little bit of math in the process.